Welcome to NASA's Jet Propulsion Laboratory in Southern California. NASA's Perseverance rover started the science phase of its mission back in June. Now, it has successfully acquired its first rock samples of Mars. I'm Raquel Villanueva of JPL's Digital News and Media Office. I'll be your host today as we discuss collecting Martian samples that are planned to return to Earth. Those of us here at JPL are all masked in accordance to LA County guidelines here in California. Our speakers today include, from NASA headquarters, Lori Glaze, Director of NASA's Planetary Science Division, and here at JPL, Jessica Samuels, Perseverance Surface Mission Manager, Matt Robinson, Perseverance Strategic Sampling Operations Team Chief, Katie Stack-Morgan, Perseverance Deputy Project Scientist, Yulia Goreva, Perseverance Return Sample Investigation Scientist, and joining us virtually is Meenakshi Wadhwa, Mars Sample Return Principal Scientist. We'll be taking questions during the briefing, so if you're a member of the media on the phone lines, press *1 to be put in the queue. If you're on social media, use the hashtag AskNASA. And I'll now turn it over to Lori Glaze.
Thank you, Raquel. I am excited to be here today to talk about just how important it is for us to collect and analyze these first Martian rock samples for return back to Earth. You know, at NASA, we get to see a lot of things that rewrite the history books. And what occurred September 6th at Jezero Crater is right up there with any of them. I'm happy to say that not one, but that the first 2 samples of another planet are prepped and stowed as the first official candidate samples to be returned to Earth by a future mission. NASA's team leading that next mission, called Mars Sample Return, is thrilled about this achievement and what can be officially declared as the start of the Mars Sample Return Relay. The Mars Sample Return mission is a strategic and bold partnership with the European Space Agency and will be the first sample return mission from another planet. A bit later, I'm excited to hear Dr. Meenakshi Wadhwa detail the significance of bringing those samples back to Earth. One of the reasons we explore Mars is because it holds a rock record that's been untouched for about 3.5 to 4 billion years. And here on Earth, we have plate tectonics. Our planet's crust has broken into large, blocky plates that churn, shift, compress, and expand over and over. And what we see today on Earth's surface is not at all the same as what Earth was like when it first formed. But Mars doesn't have plate tectonics, and so its early history is well preserved in the layers of the rocks on the planet's surface. And Perseverance is playing an incredibly important role in our understanding of Mars and demonstrating key technologies as we take our next steps in exploring the solar system. If I could have my first graphic, please. Just want to emphasize that everything we do builds on what we've learned before. We stand on the shoulders of the giants to be where we are today. From the left here, beginning with Sojourner, our very first foray into roving on Mars in 1996, through the Spirit and Opportunity rovers, through Curiosity, and now Perseverance, and then on to the Mars Ascent vehicle that will begin the journey to bring these samples back to Earth, all feeding forward to the eventual human exploration of Mars. As we head into this amazing future, we know that even though some of its rocks are not, Mars is hard, and there will be trials along the way for both this team and for future missions. But the scientific return is worth every challenge, and we've made unprecedented progress. And now I want to hand things over to Jessica Samuels, who will walk us through what Perseverance has been up to.
Thank you, Lori. So we are currently on our 198th sol, or Martian day, in the mission, and happy to report that the vehicle continues to be healthy with all of our systems operating nominally. To give you all a little reminder of where we are in our sol path here, let's look at this first graphic. So to date, the rover has traveled 2.2 kilometers, or about 1.4 miles. And if you follow the path leg south, you can find the location of our first sampling attempt at Rubion. As we continued our leg to the west, we were very pleased to see our enhanced autonomous navigation system performance travel about 560 meters in just over the course of 2 weeks while performing remote sensing along the way. So we are well on our way with a fast traversing vehicle on Mars, making great strides. But let's talk about the sampling. So let's see, our next image here. So this is an image of our first sampling location. Our target Rubion is on the right, and you can see this is a paver stone. And while we failed to acquire a solid core at this location, we believed it to be a result of the actual properties of the target. But we also needed to make sure that we didn't have a problem with the sampling system itself. So the engineering team, working with the project science team, sought out to reach a new target, and we nicknamed this target. We found a target which we believed to be less weathered and more robust, and nicknamed the target Rochette. So in this next image, you can see this target Rochette, and you can see the robotic arm placed on that target. Now, prior to sampling, we go through a series of pre-sampling steps. And here, you can see that the Watson image is actually observing different locations on the target to assess where we may want to core. On the right side of the image, you can actually see the coring tool, and it currently has an abrading bit installed. Now, we use this abrading bit to create a 5-centimeter patch and remove a few millimeters off the top of the surface so that we can see the internal structure of the rock and evaluate its composition with the science instruments that we have on board. Now, after reviewing the abrasion of this target, which we can see in this next image, the engineering and sampling team felt quite engineering and science team and sampling team felt quite confident about proceeding with an acquisition in this rock. And as Lori mentioned, not only did we core and acquire and store one sample, but we acquired 2 rock core samples. As we were evaluating this target, the science team found this target to be a very high value as well, and we proceeded with our paired sampling strategy. And the second sample was acquired just 2 days after we acquired our first sample. So the height of each of our 2 rock core samples, the first was 5.9 centimeters, the second 6.1 centimeters, and with a target depth for acquisition being 6.6 centimeters, you can imagine we were all very, very pleased with these results. The volume is measured by an internal station inside the cavity inside the rover itself. So personally reflecting on this moment, this has been the culmination of so many years of so many people's hard work and time and effort. And I know that when I joined this particular project in 2014, I wanted to be a part of this moment, to be able to achieve something that has never, ever been done before. And while it definitely was a very long time waiting, I think all of us can say that it feels fantastic to be able to be up here and share this all with you. But of course, building spacecraft and operating them on Mars does not come without its challenges. But these are the challenges that keep us all going and motivated to do what we do. You know, whether it's building a piece of hardware and finding that it doesn't do what you intended it to do and you need to redesign it during development, or schedule slips because that's just how long it takes to perform the work, or having Mars react to you in a way that you never experienced in your ground test program. These are the challenges that continue to make us better engineers, better scientists, and better teammates. Like our Perseverance rover, this team continues to persevere and maintain the confidence in our engineering capabilities, as demonstrated now with our 2 sealed rock core samples. We all take significant pride in continuing to do things that are hard and challenge ourselves. But we know, and as demonstrated by what we have just done, that continuing to work as a team, we really can achieve these amazing accomplishments. So to tell you a little bit more about how our sampling system works, I'd like to introduce you to Matt Robinson, our Strategic Sampling Science Team Chief.
Thank you, Jessica. The sampling and caching system is the most complex mechanism ever flown into space. However, it's the appropriate level of complexity for the job that we've asked it to do. And so far on Mars, it's performed absolutely beautifully. The robotic arm has a coring drill on the end of it. It places and preloads the drill on the rock target. As the coring drill drills into the surface, the sample enters a sample tube. And here's an example from our test program of what the sample tube looks like. Start the video, please. Then the robotic arm retracts from the surface and drops off the drill bit with the now filled sample tube into our sample processing center. There's a sample handling arm which manipulates the sample to take images of the sample, to measure its volume, to seal the sample tube, and then to store it on board for potential future return. In our first attempt to acquire a core at target Rubion, we commanded the sampling system to acquire and process a sample on the same sol or Martian day. For our second sample attempt at target Mont Denier, we wanted to do things a little bit differently. And what we did was we acquired the sample first, or attempted to acquire the sample first. We then paused before processing the sample so that we could confirm that there was a sample in the drill and in the tube. So next image, please. So if we look at the images on the left and the right, these images were acquired after we picked up the sample, but before processing. On the left, you can see a beautiful image of the core within the bit and tube. But on the right, it's not so clear that we actually have a core in the bit or the tube. So what happened between the left and the right? And the answer has to do with our process for acquiring a core. When the drill breaks off the core to capture it, sometimes we get a little piece of rock stuck between the sample tube and the drill bit teeth. In order to mitigate that, we point the drill bit at a bit of an angle, and we perform a couple brief percussion activities to try to either shake that little piece of rock out of the bit or to force it down into the tube with the rest of the core. The image on the right is after that procedure was executed. So when these images came down, and we took a look at the one on the right, we knew one of two things had to have happened. Either our core sample was ejected out of the bit during that percussion activity, which we thought was highly unlikely, or our core sample slid down into the tube and we just couldn't see it due to the lighting conditions. So in order to not process an empty sample tube, what we decided to do was take an extra day, acquire additional images under better lighting conditions, just to verify that we had a sample. So just imagine we had a couple days of being anxious. We then met in our command center. We were huddled around our computer, waiting for the images to come down. And then the next image, please. And then this is what we got. We were rewarded for our patience. So you see an image looking down the drill bit into the tube, and you see a beautiful core there. And at that point, our team was just absolutely ecstatic. I don't have words to say how we felt. Many of us have worked 8 years or more to design, build, and test this system, and this was just the fruition of our efforts. and we were just thrilled that it worked. But our job wasn't quite done. We had to process the sample. So we gave the go-ahead to proceed with processing the sample. Next image, please. So what we see here are a series of images at our vision station within our processing center. And you can see, as we move the tube up into the camera, our sample comes into focus. This is the absolute best view that we have of the bottom of the core. And we're rewarded once again with an absolutely beautiful image. After that was finished, we then had to seal the sample. Next image, please. So this is a before and after of the sealing process where we could see that it was activated. These images were taken again at our vision station. And then finally, we stored the sample on board. Now, the resulting core that we got was roughly 6 centimeters, which is about 2 inches, and it would look probably something like this one. This is a sample from our test program here on Earth. Well, Mont Denier was our first sample acquisition and processing. A couple days later, we processed our second sample at Montagnac on the same rock. But our job's not done. We have an additional 35 sample tubes to acquire samples and to process. So we have a ways to go, but we're excited to have the opportunity and we're thrilled to have the challenge. And with that, I'll pass it on to Katie.
Thanks, Matt. On behalf of the Mars 2020 science team, I would like to thank and acknowledge the thousands of engineers and scientists who contributed to this major mission milestone, an important next step in planetary exploration. Since the Apollo astronauts brought back samples from the moon to Earth, scientists have eagerly awaited Mars sample return, knowing that samples from Mars could provide answers to some of the most fundamental and tantalizing questions about the origin of life beyond Earth and the evolution of planets over time. Perseverance's accomplishments this week, including the successful acquisition of its first rock sample, Mont Denier, and its pair, Montagnac, show that we are well on our way to accomplishing Mars sample return. In addition to collecting samples, Perseverance has an important role to play in Mars sample return, providing the geologic context for the samples it collects. Perseverance uses its science payload to build that context, building up the field notes and observations that will enable future scientists to better understand and interpret these samples. Today, I'll share with you what we know about the geologic context of the first samples that Perseverance has collected and why we were confident that this week's sample activities would be successful. So we'll begin with an orbiter's eye view of Jezero Crater in the first image. We can see here the rover's landing site at Octavia E. Butler Landing, shown there in blue, and the rover's current location in green. Since landing, Perseverance has been exploring the rocks of the present-day floor of Jezero Crater. Scientists have long debated whether these rocks are sedimentary, perhaps related to the ancient lake in which the Jezero Delta was formed, or whether they were the result of volcanic activity in the region. Regardless of whether these rocks are sedimentary or volcanic, they've been of interest to the Perseverance team because they include both some of the oldest and amongst the youngest rocks in Jezero Crater. And these rocks have the ability to provide important time constraints and duration constraints on the Jezero Lake and its habitability, and aid in our construction of the geologic history of the region. Zooming into the rover's traverse thus far, as seen in the next image, we can see, as Jessica mentioned, that after the rover landed, we began traversing south, carrying out a dedicated campaign to study the rocks of the crater floor. We attempted our first sample of these crater floor rocks at a location called Rubion. Rubion happened to be one of the lowest elevation places traversed by the rover, which could have offered us our first clue that these rocks were weak and perhaps particularly susceptible to erosion. When our first sample attempt didn't go quite as expected, we decided that our second attempt should be in a setting that was very different, with rocks that had very different material properties. We then turned our attention to the resistant rocks up on the capping the cliffs and ridges nearby and past Rubion. We ended up traversing our 2B Ridge, a feature shown here in this image, and ascended the top of our 2B Ridge where these massive capping rocks occurred at a location called Citadel. When we arrived at Citadel, which we can see in the next image, this is the view that we had. We saw a series of blocks organized into a layer dipping about 5 degrees to the south. Although these rocks have been slightly displaced, they probably haven't moved too far from their original location. We were searching for a strong, hard rock that was big enough for both an abrasion as well as up to 2 drill targets. We found what we were looking for in a rock that we called Rochette, which you can see annotated in the next image. A side-by-side comparison of Rubion, the place of our first sampling attempt, and Rochette, where we successfully cored this week, can be seen in the next image. What we have here is Rubion on the left side, and we can see that this outcrop is low-lying and flat with rounded edges and a rubbly, crumbly surface texture. On the right, we have Rochette. It's standing up from the ground and has hard, angular edges, characteristic of hard rocks as we know them on Earth. And so we were thinking that also, if you look at Rubion, we can see that it is breaking down into pebble-sized grains. In contrast, Rochette is relatively smooth with flutes and grooves on its surface, suggesting that it has survived billions of years of wind erosion. Based on the observations that we have so far, we tentatively interpret Rubion and Rochette as ancient volcanic lava flows. We base this interpretation off of the lack of sedimentary textures, obvious sedimentary textures in the rocks that Perseverance has explored thus far, and in fine-scale textures that Yulia will talk about in a moment. Volcanic rocks are an exciting addition to Perseverance's sample collection because volcanic rocks have the potential to tell us about the interior and interior workings of planets and are particularly good for providing the ages of rocks. An interesting thing about these rocks as well is that they show signs for sustained interaction with groundwater. If these rocks experienced water for long periods of time, there may be habitable niches within these rocks that could have supported ancient microbial life. Because these rocks were of such high scientific potential, we decided to acquire 2 samples here at Rochette. The Mars 2020 science team has a plan to acquire and to place down 1 or more sample caches. And so to ensure that each of these sample caches are as complete as they can be, we have a strategy to acquire two samples at each of our highest priority sampling locations. To tell us more about these rocks, what they're made of, what they look like up close, and what that means geologically, I'll now pass it off to our return sample science mission scientist, Yulia Goreva.
Thank you, Katie. Well, the first slide, as Katie showed, compares 2 drilled boulders. And visually, the rocks indeed on the left seems crumbly, and the second on the right is high-standing, much more solid with sharp angular edges. As both Jessica and Katie mentioned, we use Rover's drill to abrade the rock and expose the fresh and dust-free interior of it. Just like geologists in the field, when we want to see the interior of the rock, we take a hammer, we smack it down, open it up, and see this fresh surface. So we use these abrasion patches, and next slide, please. These abraded patches to, as this freshly exposed surface, to look at the texture and chemistry of the rock using our onboard instruments. The next slide is a natural color close-up of a part of Bellegarde. That is our recent, the most recent abraded patch made by SuperCam instrument. SuperCam uses optical and laser spectroscopy to identify chemistry and mineralogy of the rock. The image of Bellegarde here shows that the rock consists of several mineral phases. You can see them by color. They are light, white, dark, grayish, and somewhat rusty color. The overall chemical composition of Bellegarde is consistent with minerals typical for an igneous or volcanic rock. The rock originally solidified from lava or magma, such as basalt or gabbro. But in addition, Raman spectrometer of SuperCam identified a salt within the rock. And you can see that white speck right in the middle of the image. Further imaging by Sherlock instrument, you can see in the next slide, that instrument is placed within only a few centimeters from the rock surface. And it gives us even more detail. You now can see individual crystals, and some of them are angular or elongated, we call them tabular, and not rounded as you would expect in sedimentary rock. That observation further supports the hypothesis of the rock's igneous or volcanic origin. So let's zoom even closer. The blue square in the middle is a footprint of Sherlock's spectral analysis, and it's only 6 by 6 millimeter in size. The next slide shows that footprint. You really can see individual crystals here. And while the detailed mineral analysis are still ongoing and the science team working and poring over the data that is supplied by our Perseverance rover, Sherlock spectroscopy results reveal the presence of salts as well. Salts such as calcium sulfate. Those are yellow dots in the image. The calcium sulfate is something like gypsum or relative to gypsum. And a calcium phosphate. Those are the blue dots. Now, next instrument, Pixel, identified over 20 elements in Bellegarde. The maps, like you see on the slide, same size as the Sherlock's map, show the chemical composition of each individual mineral grain from which mineral, actually real mineral, can be inferred. Here is shown a spectral signal from calcium in red, sulfur in green, and aluminum in blue. Combination of calcium and sulfur in the same spot indicates a calcium sulfate, yellow color in this image. And that location for sulfate and composition correlate directly with Sherlock findings. So what does this actually mean? What it means that we have collected a rock from the floor of the geyser crater that is igneous or volcanic in origin, and it has salts within it. The presence of salts indicate that this rock was subject to water. The water percolated through the rock, and as it percolated and evaporated afterwards, it's left behind the salty residue. And why the science team is excited about that is because this rock, once returned to Earth, once returned to state-of-the-art laboratories, it can be really interrogated for its chemistry, for its mineralogy, for its age. And salts within it, we can look at the composition and look for tiny inclusions, such as tiny inclusions of liquid bubbles or bubble fluids inside of salts. That would actually give us a glimpse of the geyser crater at the time when it was wet and was able to sustain an ancient Martian life. And with that, I'm back to Minnie, or forward to Minnie.
Great. Thank you, Yulia. So I know you've heard this from others on the panel today, but I cannot overstate the significance of these rock samples that were collected by Perseverance. This is a truly historic achievement. You know, the very first rock cores collected on another terrestrial planet. It's amazing. These two rock cores, as well as actually the first sample tube that contains Martian atmosphere, these actually represent now the beginning of Mars sample return. I have to say, you know, I've dreamed of having samples back from Mars to analyze in my lab since I was a graduate student. And, you know, in our science community, we've talked about Mars sample return for decades. And now it's actually starting to feel real. These first core samples will actually be among tens of other samples that'll be collected by the Perseverance rover in the many months and years to come. And the point of collecting these really well-documented rock, soil, and atmosphere samples, though, is to bring them back to Earth so that we can analyze them here in the best and most capable Earth-based laboratories so that we can answer some of humanity's biggest questions, like, was there ever life beyond Earth in our solar system? Did life exist on ancient Mars?
Besides these astrobiological questions of interest, these samples will also give us a much better understanding of the geologic history and the history of water and climate on Mars. And so by returning these samples, we'll be able to definitively address some of these high priority science questions by engaging the global community of scientists in their analysis using state-of-the-art analytical capabilities like this synchrotron radiation source facility that's shown here in the next image. And this type of facility actually occupies the area of several city blocks. It produces high energy, high brightness X-ray beams that can be used to provide some unique chemical and mineralogic information for natural samples on extremely small spatial scales that are just not possible if you do these types of analyses or you try to do these types of analyses remotely. So this is not something you can really take to Mars on any kind of spacecraft. This is just an example of the many types of advanced techniques that are available in Earth-based laboratories that you'd never really can send to Mars because of mass volume and power considerations. But such techniques can and will be used for analyzing return samples. The other reason that we want to bring back samples from Mars is that if we curate these samples well, we'll be able to analyze them in the future using techniques that don't even exist today, and address questions that perhaps we can't even think of asking based on what we know today. This next image actually shows a sealed rock core that was collected on the moon during the Apollo 17 mission nearly a half century ago. This sample was carefully unsealed last year in NASA's Lunar Curation Facility, and it's now being analyzed by a new generation of researchers using techniques that didn't even exist in the 1970s to answer questions about the moon that could not be answered back then. For example, is there water in the interior of the moon? And if so, how much? So it's really amazing, in fact, how much we can continue to learn about the moon and about the Earth-Moon system and about our solar system from analyzing these lunar rocks that were collected nearly 50 years ago. So the samples that we bring back from Mars will also enable incredible discoveries for decades to come. So the next animation actually illustrates that the samples collected by Perseverance represent the first phase of the MSR campaign, or the Mars Sample Return Campaign. The next phase will involve collecting these samples and launching them into orbit around Mars. And then these orbiting samples would be captured and returned to Earth in a sample return capsule. So you can see this animation here showing the sample return capsule that would then be sent towards Earth. So this next phase is planned to begin no sooner than 2026, and the samples are expected to return no sooner than about 2031. So I've no doubt that the samples that we collect on Mars with the Perseverance rover and that we bring back to Earth in the next decade or so will revolutionize our understanding of Mars as a terrestrial planet, including whether life once existed on that planet. And with the collection of these first samples by the Mars 2020 mission, we're taking our very first steps towards that goal. For myself, I can say that I can't wait to analyze these samples in my lab at Arizona State University, and I know many scientists around the world are eagerly waiting for these samples too. So the fun is just beginning, and stay tuned. So back to you, Raquel.
Thanks, Meenakshi. We'll now move into Q&A. Now, remember, if you're a member of the media on the phone line, you can press *1 to get into the queue. And if you're on social media, you can use the hashtag AskNASA for any questions. Now, on the phone lines, we have Paul Brinkman from UPI.
Hi, thanks very much. This might be jumping ahead a little bit, but in terms of the next steps for the mission, can you explain how and when you will decide to deposit samples on the surface? And is there any specific number of samples that you intend to collect before that first drop? Or will that be more dependent on the location of the rover? And I'm not sure who is the right person to direct that to, so whoever wants to.
Yeah, I can take that one. Yeah, so for the prime mission of Perseverance, we plan to continue exploring Jezero Crater. That prime mission is 1 Mars year, about 2 Earth years, and the qualified lifetime of the rover is about 1.5 Mars years. So we plan to explore Jezero for that period of time. I think around that time, we may be in a position to deposit our first cache of samples in Jezero. And so that's about the time frame that we're looking for. And we have a ways to go, of course, before we do that. And when that time comes, we'll make decisions based on what the sample collection is in the rover at the time, what we'd like to put down in that first cache, and perhaps which samples we'd like to continue carrying with us.
Great, thank you, Katie. And next on the line is Mike Wall from space.com.
Thank you all for doing this. And yeah, it's a really big moment. So I just want to say, first of all, congratulations. And this is probably for Matt. Doing those two sampling operations back to back and finding both of them were successful. Do you feel like, I mean, I know it's a small sample size, if you'll pardon the pun, but like, do you feel like you really have it down now, or do you need to do some more tweaking to like really understand this process? Could you just give us an update on where the sampling team stands about how the process is sort of going and what further tweaks need to be made? Thanks.
And that's a great question. One thing this is actually my third sampling mission, and one thing that I've learned is that Mars always can throw you curveballs. So we will continue to look at potential analog samples for the rocks that we've seen so far, and to test those in our test lab and to tweak our algorithms that perform the sample acquisition. I think science would potentially like to go back to Rubion at some point and maybe acquire a sample. So we would like to figure out how we could potentially acquire that sample. So we will investigate a test program to look at analogs that we can enter to attempt to successfully acquire a sample at Rubion. You just never know what you're going to encounter as we proceed through the mission.
Thank you.
Thank you. And up next is Issam Ahmed with AFP.
Yes, hi. Thank you so much for doing this. My question is, we got the press release a few moments ago, and we had a very nice quote there from Ken Farley saying that the first rocks reveal a potentially habitable, sustained environment, and it's a big deal that water was there for a long time. Could you perhaps talk to where we were scientifically about the habitability of this environment before, and how much these samples have advanced that?
Yes, I can take that. Yeah, thank you. I can take that question. So I believe every single surface mission to Mars has observed what we believe to be an ancient habitable environment. This was particularly hit home by the Curiosity rover mission, which discovered within the first year of its mission a conclusively habitable lake environment. And we knew already that Jezero crater had such a habitable lake environment, and that's what brought us there to Jezero. But the big difference here is that now we have a sample of potential habitable environments ready to come back to Earth. And the mineral diversity of this sample that Yulia talked about, the presence of salts in these rocks. Salts are great minerals for preserving signs of ancient life here on Earth, and we expect the same may be true for rocks on Mars. And so the major advances, I think, are still to come when we get those samples back to Earth and can look into that rock sample, whether it's Montagnier or Montagnac, and look for those signs of ancient life in some of these what may be habitable areas within these rock samples.
Thank you.
All right, thank you. We now have some social media questions. For Loop on YouTube asks, how did you prevent acquired samples from cross-contaminating, considering the same bit is used to drill all of them? Jessica, Matt, would you like to take it?
Either way. So our system is designed to reuse coring bits. We actually have a series of coring bits on board so that we will change out bits over time. But we also have quite a dynamic environment that happens as we perform the percussion activity within the sample tube that sits inside of the bit, as well as cleaning events that we do periodically for the core itself. Matt, I don't know if you want to add to that.
The only additional thing that I would add to that is that we carry multiple drilling bits with us. So we have a total of 6 drilling bits. And if there was a special sample that we wanted to acquire and we wanted that to be a little more pristine, we could potentially use a fresh drilling bit for that one.
And Yulia also has a comment.
And I'll follow up from a science point of view. We are collecting samples on Mars. The cross-contamination between the samples is not that big of a concern because we have dust everywhere. The dust covers the Martian surface. It's going to get in every tube that we are going to acquire our samples in. What contamination really plays, or contamination control plays a really big role is in how we designed and prepared the hardware for collection of the samples. The concern here is that we didn't want to bring anything from Earth that could be mistaken by Martian organics, for the organic material, once it's actually the sample is back to Earth. And for that, for years, the Mars 2020 team went through a great deal of development of both materials and the cleaning procedures for that hardware, so we can assure that there is no terrestrial contamination in the samples. But with respect to cross-contamination between the samples, that's not that big of a concern for science.
Thank you all for all your answers. And we have another question for Lori Glaze, but I'd like to open it up to everyone else after her answer. Ciencia News on YouTube asks, what is the importance of collecting this first sample?
I think we've heard a couple of times today just how important it is to collect this first sample. This is the first time we have ever collected a sample of a rock from another planet with the intention to bring that sample back to Earth where we can analyze it. And it's not just the scientific importance, but the technical achievement to be able to do this. I think Jessica said that this is perhaps the most challenging thing we've ever tried to do on another planet. The complexity of that system, of the sampling arm and the drilling apparatus, and then the ability to process the samples and cache the samples on the rover, is something that is incredibly complex. And it has an amazing potential to help us better understand the history of Mars, but also potentially the possibility for whether or not life existed on Mars in the past. So it's an incredible opportunity. And of course, we already have samples of Mars on Earth as meteorites, which I'm sure Minnie can add to here and speak about. We have pieces of Mars on Earth, but we don't know where they came from. We don't know the context. We don't have all of that basic information. And so this is just an amazing opportunity.
Would anyone else like to add anything? All right, Lori
Maybe
summed it up.
I can.
Oh, go ahead, Minnie. Go ahead.
No, I was just going to say that Lori really put this very well. But and we have these Martian meteorites, but these meteorites have, by their very nature, they've been sitting on the Earth and bathed in the Earth environment for sometimes many decades or longer. And so we don't have really unaltered, pristine, unaltered by Earth contamination, materials from Mars. And so these samples, when they come back to us, they'll be just incredible in terms of being able to tell us something, especially about whether there was any kind of past life on Mars, and also important questions about the evolution of Mars, its history. And so, for me, that it's really these first samples are really important because they really kind of kick off that Mars sample return campaign. And so, yeah, I'm super excited about that.
And I actually have a follow-up question for you. Wilco on Facebook asks, how do the samples return to Earth?
Yeah, so that the Mars Sample Return Program is currently in its concept and development and technology development phase, and so we're in phase A right now, and we're really planning. What we're planning to do is to launch a couple of missions. One will be a sample retrieval lander, which will actually pick up the samples that'll be collected by the Perseverance rover and bring them into Mars orbit. And then there's an orbiter, the Earth Return Orbiter, which will be basically be capturing these orbiting samples and then return those back to Earth in an Earth return capsule, as was shown in the animation that I showed. So there's going to be a couple of these missions that are hopefully going to be launched in no sooner, as I said, in 2026, and hope to get these samples back perhaps as early as 2031.
Great, thank you. And up next on the phone lines is Marcia Smith from Space Policy Online.
Thanks so much. I had two questions for Lori, and one has to do with what Minnie was just talking about in terms of the schedule for getting this done. Does NASA have all the money it needs in its budget runout to support a launch in 2026? And when are you going to decide if it's going to be 2026 or 2028? And then a very different kind of question is, what do you do with these scientific results as part of NASA's plan to send humans to Mars someday? If you find that these areas are habitable, does that mean that you're not going to send astronauts there because you don't want to contaminate the area, or you will send astronauts there because that's exactly what you want them to study?
Marcia, those are two great questions. I'll start with the first one. So as Minnie said, we are in the phase A of the development right now, the concept development. We are extremely pleased with the budget request that the president put forward for fiscal year 2022 and beyond. And I think we are in a really good place right at this moment with the funding that we have. Of course, as part of phase A, we are exploring a bunch of different trades and trying to best understand how we can execute this mission. So I think we're where we should be right now. As far as the human exploration question, I think the human desire to put humans on Mars is very strong. That exploration drive that we have. I really believe that we are going to do that one way or another. And once we better understand the environment on Mars and better understand whether or not there was potentially life there in the past, will help us design where we want to go and how we want to go. But I think it's definitely going to happen.
Great, thank you. And up next is Leo Enright with Irish Television.
Thanks very much, Raquel. This is for Katie. Katie, you were talking about the high scientific potential of this sample, and I'm assuming the fact that you're now talking about perhaps going back to Rubion means those words were chosen quite deliberately. Can you be a bit more specific about why you're excited by this sample? In particular, does this unequivocally say that the lava flow predates the delta itself, and the fact that the lava does have these salts in it, is that what is getting you excited?
Yes, thanks for that question. So first of all, we're excited about these rocks, whether it was Rubion or Rochette, because volcanic rocks have the potential to provide age constraints on the Jezero Delta. And there have been different models for what the age and relative age of the crater floor rocks are with respect to the delta. But I think the current prevailing idea is that these rocks of the crater floor perhaps are just older than the delta. So if we were able to get an age for these crater floor rocks that we've just collected, we would be able to put no older than date on the timing of the Jezero Lake. And that would be an incredibly important thing to understand, especially if we go forward in the mission and as we search for signs of ancient life in those delta rocks. We also mentioned, and Yulia talked about, and I'll pass it to her in a moment, our excitement about the mineral diversity of both the Rochette samples as well as Rubion. And Rubion was an interesting rock because the thing that makes it most interesting might have also made it one of the things that was made it difficult to acquire and to core. And so at Rubion, we had a lot of salts there, and Yulia talked about the significance of that. And so I'll pass it to her to talk a little bit more about why we were particularly excited about Rubion and the extent of alteration that rock saw, but why we also think that Rochette is an important sample to have in our sample collection.
Well, Katie, you pretty much answered the question, but the importance is that the rocks in general, Rubion and Rochette, are very similar, if not the same. But they did experience different degrees of the aqueous alteration or different degree of exposure to water. Rubion has much more salts that we observed with our Rover instruments, and much more alteration, which is changing the minerals within the rock, within the volcanic rock, with exposure to water. And as such, that rock has even bigger potential to deliver the sample that is full of those salts that may have the inclusions of liquid water within them that we actually can look at and learn about the wet time in the Jezero history. And at the same time, it is still an igneous or a volcanic rock and potentially provides information of age, especially in combination with the field observations that Katie was talking about. We don't take just the rock and learn about its chemistry. This is a rock in a context. So we look at the relationship between different units, which one is older, which one is younger, how they relate to each other. And these are all field notes and observations that we are taking as we are on the surface of Mars. And the sample is to test that hypothesis and to provide the data once it's back on Earth.
Great, thank you. And up next on the phone lines is Ken Kremer with Space Up Close.
Hi, thank you for doing this, and congratulations on the core sample. My question, I think, is for Katie Stack-Morgan, but for anyone else, too. Can you talk a little bit about the future route that the rover is going to take? And when do you think you will get to the stromatolite region, which was your main target, and where that is located? Thanks.
Yes, great question. So we are just planning today a drive away from the Citadel region where we acquired these 2 core samples. And we'll be heading into a region that we call Seta. And we think what really is exciting to us about this area are 2 main things: the potential that this area has fine-grained sedimentary rocks, and we see layering that suggests that that could be true. We also see in this area a very distinct olivine signal in the orbital spectroscopy data. And there are only very specific types of rocks that we have here on Earth that have such olivine signals and olivine-bearing signals, and so we're excited to check out those rocks, which also may be amongst the oldest that we have exposed in the crater. After we go to South Seta and do what we hope to be sample collection there, we'll then go around that outcrop, that big area exposure, and head straight to the delta. And we will begin our exploration of the delta. And you mentioned stromatolites. So now we don't know for sure that there are stromatolites or ancient fossilized microbial mats here in Jezero, although it would be certainly fantastic if we were to find something that we thought could be that. The Jezero Delta itself, particularly the lower layers that we think were deposited in a very quiet, calm lake environment, are a great place to look for potential ancient biosignatures. And so we will have the opportunity to explore that once we get to the delta. And you might also have been referring to what we've been calling the marginal carbonate unit within Jezero. And these are the deposits around the inner rim of the crater. And carbonate minerals here on Earth are also great preservers of ancient biosignatures, and many stromatolite examples are found in carbonate-bearing rocks. And so after we explore the delta, we'll likely move on to the marginal carbonates, and that will probably be around the time of the end of our exploration of Jezero crater, and perhaps beyond that, we'll be able to think beyond the crater.
Thank you.
Great. We have another social media question coming in, and I think, Matt, you should get your sample ready. How large are the samples that have been collected, and do you expect that will be returned intact in that full size?
So this is a core sample from our test program and our test bed on Earth as we were developing our sampling system. It's roughly 2 to 2 1/3 inches long. All the core samples aren't going to look quite as intact as this one. They may break up into little chips, but this is representative of a particular rock sample. But even if it breaks up into little chips, it's still a very scientifically valuable sample, and they can still do a whole lot with it, and it's still very interesting. So you wouldn't expect all the core samples basically to look quite like this as one solid piece. But we do expect them to be about the same length of roughly about 2 inches or so.
Thank you. And that is all the time we have for questions today. I'd like to thank all our panelists for joining us. And for more information on the mission, visit nasa.gov/perseverance and mars.nasa.gov/perseverance. You can also check out the latest raw images being taken by the rover at go.nasa.gov/perseverance-raw-images. And don't forget to follow us on social media at NASA Persevere. Thanks for joining us today.